So now just making some room to write a little more here. Okay, so now what this tells us is that if you work it out, it's as though, you know, as the slinky is precessing, as it's rotating, it's as though its velocity is proportional to k. Okay, so why is that? Well, you see, we already said that the period of this function, the period of the wave function is 2 pi over k. And if you look at this, you know, this time dependence, e to the I k squared t, the time it takes for this, you know, as this wave function is precessing, to precess through one full cycle, is actually 2 pi over k squared. And so the apparent movement of this slinky in one such full rotation of the phase is 2 pi over k, but this happens in time 2 pi over k squared, so the apparent velocity is this over this. So it's 2 pi divided by k over 2 pi divided by k squared, which is k. Okay. So now what we've understood is, if our wave function looked like this, if it looked like e to the ikx, then it would have a definite velocity of k. Okay. But we are not given, you know, but we are given just some psi of x t. It's not e to the ikx. You know, this is the wave function which had a definite velocity of k. So now we can ask, what's the, you know, if we were to write out psi of xt in the velocity basis, right? So we could write it out in this velocity. Instead of in the position basis, we could write it out in the velocity basis, and we might have some superposition which, you know, which look like that, which would say, with what amplitude is the velocity of this particle at time t equal to v? And the answer would be it's this much, right? So this is amplitude. Okay, so let me call it phi of v comma t. So this is the amplitude with which it has this. And so how do we compute phi of v comma t? Well, it's exactly the component of psi in the direction of this function. So how do you compute the component of psi in this direction? You take the inner product. The inner product of this function with psi of x comma t, which is what? It's the integral of e to the minus ikx. It's the complex conjugate of this, psi of x comma t dx, minus infinity to infinity. Right? What's the inner product? It's just you just take the product of the corresponding components, well, with the complex conjugate of the first one times the component of the second one, and then you add it over all, you know, over all the dimensions. But here we are working in a continuous dimensional space where x is what indexes these dimensions, so we just take complex conjugate of the first times the second, and instead of summing over all the dimensions, now since x is continuous, we integrate this from minus infinity to infinity, this times dx, and that's the component in this direction. But now some of you might recognize this function. What is this? Well, phi is just the Fourier transform of psi. Okay. So, well, I'm calling it velocity here just for, you know, just for intuitive purposes. You know, in quantum mechanics, we are really measuring momentum, which is proportional to velocity. And so momentum is the Fourier transform of position. So position and momentum are related to each other by Fourier transforms. This is a very interesting thing, because what it says is you start with some superposition, psi. So this is psi of x. This is our position of the particle at whatever time, right? It's some function, right? This is psi of x. Now we write phi of p for momentum. Okay, so this is, okay, let's write it in blue. It's phi of p. Okay, this is going to be some other superposition. And what I'm claiming is that the way you get from one to the other and back is by doing a Fourier transform. Okay, so now what do you know about a Fourier transform? Well, one thing you should know is that the more you concentrate a function in the primary domain, the more it spreads out in the Fourier domain. The more you try to concentrate it in the Fourier domain, the more it spreads out in the primary domain. So what are you to do? Well, it turns out that the best you can do is sort of make this function on this side be a Gaussian with some standard deviation sigma. And then you have some corresponding standard deviation sigma hat on this side. And it turns out that the smaller sigma is, the bigger sigma hat is, and vice versa. And so you can try to find a happy medium between the two. And this is what gives us this uncertainty principle, which says that delta x times delta p is at least h bar over 2. So delta x is really sigma, delta p is sigma hat. And what the fact about Fourier transforms is that the way you minimize this product is by using Gaussians in the first place, and then in the second place, if you use Gaussians, then the width of this Gaussian times the width of this Gaussian in the Fourier transform. The product of these two widths is bounded below by some constant. Okay? So let me reiterate. There's not much of this lecture that you really need to know. But this is, this should help you get a picture of what's going on with continuous quantum states, with the Schrödinger equation for the particle on a line, with where this uncertainty principle comes from. Okay, in the next lecture, we'll look at all this in a more precise way.